Okay, we're back. Like I was saying, we have a skateboarder. He is starting from the top of a half pipe. He is skating to the bottom of it. That's a 6-meter drop. The skateboarder has a mass of 72 kilograms. So the first thing we need to do is determine if any work was done on the skateboarder by these forces: applied force, tension, or normal. Okay? There's no applied force. No one is pushing him down the ramp. A person or an animal or something has to push him down for there to be an applied force. That's not the case. There's no tension. There's no ropes attached to him. There is a normal force, however, but that normal force does not do any work. Reason being, remember, the normal force always acts perpendicular to the surface that the object is on. So right here, with a vertical wall, the normal force points to the right. But at this point, which direction is the skateboarder about to be displaced? That would be downward. What's the angle between those? Right and down? That's a 90-degree angle. The definition, the equation for work, is force times displacement times cosine of theta. Clearly there is a normal force. He is about to be displaced. However, the angle between them is 0. Or the angle between them is 90. Therefore the cosine is 0. No work is done. Even when he's down here, okay, when he's like halfway down the half pipe, the normal force would point in this direction, but he is moving right now. He's being displaced in this direction. Again, right angle, no work is done. So the normal force actually does no work on him. The normal force doesn't transfer any energy to him. It just redirects the direction of his motion. Therefore, this is no work is done. If no work is done on the system during the interaction, we go to ET equals ET. Here's initial, here's final. He ends up down here. Once again, what type of energy is present at the initial step? He's got gravitational potential energy. He's not moving yet. There's no internal energy generated yet, and there's no springs, so therefore this must be the only type of energy he has, just gravitational potential energy initially. At the end, he no longer has that gravitational potential energy, still no springs, still no friction. We said neglecting friction, negligible energy loss due to friction. He must now have kinetic energy. If you think about it, I mean, just logically, he starts up here. By the bottom, he's going to be moving faster. I'm going to do something here. I'm just going to write out both equations right here. I'm going to, write out the equations for PEG and KE right here. We want to know how fast he's moving at the bottom. MGHI equals 1/2 MVF squared. Notice what I have here. I have two terms, one on the left, one on the right. They both contain an m. If I were to divide both sides by m, that would get rid of the masses. What I'm left with is g, the initial height, equals 1/2 VF squared. Now at this stage, what I could do is I could just plug in for the values that I know. I know the acceleration due to gravity is 9.81 meters per second squared. The initial height is 6 meters. And I solve for VF squared. For VF. 9.81 times 6 divided by 1/2. Take the square root. And as you can see, the final speed of the skateboarder is approximately 10.85 meters per second. Now, the last question we could have done using kinematics, because this was a free fall question. I could have used VF squared equals VI squared plus 2AD. That is not the case here because I don't have a constant acceleration. The free body diagram for this skater on the ramp is always going to be different as he moves down the ramp. The angles and the sizes of the forces are going to change, therefore the acceleration changes. He's not in free fall here. The acceleration is not constant. I can't use kinematics to solve this. So, in a case where we can't use kinematics, we turn to energy, and we can still find the final speed of the man. Okay? I wish I had some way to demonstrate this to you. Maybe I'll work on that for a future video, but until then, we press on. Okay, some more examples on the back, more of pretty much the same sort of stuff. Number 3, a 3 kilogram box moving to the, let's just make sure we can see that good. 3 kilogram box moving to the right at 5 meters per second on a horizontal frictionless surface is brought to rest by a spring. If the spring constant of the spring is 500 newtons per meter, how far must the spring compress in order to stop the box? So here's what we have. We have a surface. It is frictionless. We have a box moving on that surface, moving this way. And we have a spring. I'm just going to attach that spring to a wall. And at some point, the box is pushing that spring in. Now, again, let's do what we were taught. Let's figure out if the applied force, force of friction, applied force, normal force, or tension does any work on these objects. The applied force, I don't see anyone pushing on the box or the spring. There's no person pushing on those, okay? Since there's no person pushing on those, no applied force here. There's no tension, there's no ropes in this problem. There is, again, a normal force, but again, the box is moving to the right. It's a flat surface. Normal force points up. That's an angle of 90 degrees between those two vectors. Therefore, the work done by that force is 0. So once again, no work is done. We have ET equals ET. Initially means before the box has hit the spring. The final spot is when the box has compressed the spring just enough so that it has stopped. Okay, that spring, think about what the spring's going to do. It's going to resist the box with a certain force, and the force is bigger as it gets compressed, so the acceleration changes as it gets compressed as well, until a point where the box stops. Now, we can't use kinematics and forces for this because the force on the spring, therefore the acceleration, are constantly changing. When you have a changing acceleration, energy is what you go with. Initially, the box is moving. It has kinetic energy, K-E-I. It doesn't have gravitational potential energy because it's not elevated at all. I mean, there's no elevation change, so we're not even going to deal with gravitational potential energy here. There is no friction, okay, no internal energy because it's on a frictionless surface, and there's no elastic potential energy because it hasn't compressed the spring yet. However, at the end, in the final stage, now it's stopped. The box has stopped moving, okay, no more kinetic energy. It hasn't gone up at all, so no gravitational potential energy. It has compressed a spring, so there is elastic potential energy in the final state, but it's still frictionless, so there's no internal energy that has been generated. What I'm going to do now is I'm going to write out my equations for kinetic energy and elastic potential energy, and I'm going to solve for what I'm looking for. How far must the spring compress in order to stop the box? What would that be? I know m is the mass, v is the velocity, k is the spring constant, how hard it is to stretch the spring, and x is the distance that the spring is stretched or compressed. Notice in my equation, just like the last example, I have a 1/2 on both sides. I don't have an m on both sides. I do have a 1/2 on both sides. Those will cancel out. I can divide both sides by 1/2. They cancel out. I end up with the mass of the box is 3 kilograms. It was moving at 5 meters per second squared equals spring constant is 500 newtons per meter. That means it takes 500 newtons to stretch it 1 meter. X squared. Okay. I solve this. I'm going to do, let's see here, 3 times 5, and that's 5 squared, so I'll multiply by 5 again. It's 75. I'm going to divide by 500, 0.15, and I take the square root, and I find that x, the distance this spring has to compress in order to stop the box, is about 0.39 meters. Okay? So we were able to find how far that spring has to compress. Interesting. We wouldn't have been able to find that using forces and kinematics. We had to use energy. Energy can tell us how far something must stretch or compress to take all of that energy. All the energy started as kinetic energy. It was then transferred into elastic potential energy by the interaction of the box and the spring. Another example, and this is a very common one, and as a matter of fact, your test, when you finally end up taking the test on energy, your test is going to have a lot of questions about roller coasters, just as a little preview. A 200 kilogram roller coaster cart is at rest at the top of the first hill in the track at a height of 60 meters. It descends the first hill and climbs up the second hill to a height of 45 meters. If the track is frictionless, how fast is the cart moving at the top of the second hill? So here's what we have. We have a cart up here at the top of the hill. We know right now that it's at a height of 60 meters. It goes all the way down. Then back to the height of the second one, which is only 45 meters up. Okay. So, once again, we check applied force, tension, or normal force. Do any of them do work? There's no applied force. There's no one pushing this. No tension, no ropes, because it's on the hill. It's just going down due to gravity. And the normal force, just like on that problem with the half pipe, the normal force is there, but it always acts perpendicular to the direction of motion, to the displacement at that time for the cart. Therefore, no work is done. And once again, we have ET equals ET. Now, this is a good case. Initially, what type of energy does it have? Well, it says it's at rest, so no kinetic energy. It says that it is at, it is above the ground, so we know that there's gravitational potential energy, PEGI. There's no springs and no friction. Again, we're assuming the track is frictionless, so no internal energy, no elastic potential energy. That's it for this one, for initially. At the end, now think about it. Roller coaster has gone down and back up to a hill of smaller height. We know that there's still gravitational potential energy, but it's different, right? It's a smaller height, therefore the potential energy has to be smaller. Which means if this is smaller than this, we've got some energy unaccounted for. So use some common sense. If it was at rest up here, goes down and then back up to a smaller height, well, it's probably moving at that point, right? There's no friction to slow it down. There's no springs to take away any energy. There's probably some kinetic energy at this point, and that is an important thing that sometimes people don't realize that, hey, you can have more than one type of energy at a time. You can have more than one type of energy at once. Okay, let's write out our equation. mg h initial, the initial height, equals mg h final plus 1/2 mv final squared. You see anything that's common to every term? That would be the m's. Those m's will all cancel out. Now, if that term hadn't had an m in it, we could not cancel it out. Please understand that fact. Because they all have m's, we can cancel it out. And I'll go ahead and plug in my numbers. 9.81 meters per second squared. 60 meters equals, again, 9.81 meters per second squared. 45 meters. Now, actually, I should have used this. I can't cancel out the g's because this term doesn't have a g in it. I can't just say, oh, that has a g, that has a g, they cancel. You can't do that. Remember, when you cancel something, you're dividing every other term by it. It's okay to divide this by g and this by g, and they'll cancel. If you wanted to do that, you'd have to divide this by g, but there's nothing to divide it with, so you'd end up with just a g in the denominator, and that's just more confusing. The term has to be in, the variable that you're canceling has to be in every single term in order for you to do that. Anyways, plus 1/2, and we're looking for v. What is the speed at the top of the second hill? Okay, so 9.81 times 60 minus, I'm going to do this in parentheses, 9.81 times 45, which is 441.45. Subtract that from our 550 something we got the last time, equals 147.15. That's the difference between this term and this term. Divide by 1/2, take the square root. We end up with a speed of 17.16 meters per second squared. Just like we said, we should have some kinetic energy at the top of that hill. Okay, so key takeaway here, you can have more than one type of energy. That is allowed. Okay, that is okay. I think I'm going to stop there, upload this, and then we're going to go and finish this last one. Okay, shouldn't take too long. So I will see you in a bit.